All right, hello everyone. I hope you are doing all right. Welcome to lesson 3.3. We're going to be talking about implicit differentiation, getting an introduction to it, and then on Monday we're going to be practicing this together, okay? Go ahead and try the do now, pause the video, try that do now, and then start the video again and check your answer. All right, so we want to take the derivative of f at pi ninths. So here's f, the derivative of f. Notice I have an outside and an inside, so this is going to be a chain rule. F prime of x is going to be negative sine of 3x times 3. That leaves f prime of pi ninths as negative sine of pi thirds times 3. All right, so then we go, okay, well, what is negative sine of pi thirds? Negative sine of pi thirds is, you go in the circle, think in your head. All right, it is, I'll just do an equal sign over here, negative square root of 3 over 2 times 3. And so we look for that as our answer over here, negative 3 times square root of 3 divided by 2. All right, just a quick reminder of the chain rule, because actually the chain rule is what we're going to be thinking a lot about today with our new kind of differentiation called implicit differentiation. So it turns out there's actually a lot of functions that can't be solved conveniently for y. All the things we've looked at so far are y equals this, right? But not all functions can be solved easily for y. Or, we might not be looking at things that are truly functions, right? We can have relationships that are not functions. They may be smooth, but we can't exactly find the slope or things very easily because maybe we have something complex like this function over here that actually has things like the natural log of x squared plus y squared minus 1 and other things worked into the equation, right? Or maybe the equation of something like a circle, x squared plus y squared equals 4, something like that. We don't really have tools to handle those things yet. So if we want to find, say, the slope of a circle, here's one. This would be a circle here with a radius of 5. Or maybe this curve right here. How can we do that? Well, the process that we use is called implicit differentiation. Implicit differentiation says, okay, I recognize in here, let's take this as an example, that I am trying to take the derivative with respect to x. I see some x's, but I also see some y's. In our head, we have to keep in mind as we work through this that y, whatever y is in here, is really some function of x, right? So if I were to take the derivative of y, it really is its own function. And that becomes the key here. So what are our steps? Well, if I want to take the derivative of something implicitly, I need to differentiate both sides with respect to x. And then I'll collect my dy dx terms on one side of the equation. I'll factor out dy dx. I'll solve for dy dx, and I'm finished. Let me show what that looks like actually in practice, because this can be a little confusing. Well, Markwalter, what do you mean that y is its own function of x? Let's try one. All right. So here is a curve here, 25x squared plus y squared. I want to find dy dx. So what does that mean? That means take the derivative of the function with respect to x. So let me start with the first term. The derivative of 25x squared with respect to x is not too bad, 50x. I just bring down the 2, multiply by 25, x, and I'm finished, right? That's for that first term at least. Plus, but then this becomes interesting. I have y squared. Now I'm trying to take the derivative with respect to x. I'm looking for variables x, but this is y. This is y, not x. So how am I supposed to take the derivative of y squared if that's not the variable I'm looking for? Well, remember that y, if I wanted to, I could solve this equation for y, and y would be some, function of x. If I were to take the derivative of some y thing, I would get dy dx, right? Okay, so let's actually treat this y squared like that. If I take the derivative of y squared, I notice that I have something squared, and then inside of that squared is a y thing. So let me take the derivative of blah squared. The derivative of blah squared is 2y. So I'm going to leave the y. And then I'm going to use the chain rule and say, well, what is the derivative of that inside thing? What is the derivative of y with respect to x? It is dy dx. So this really is a chain rule problem. The derivative of y squared is 2y times the derivative of the inside, which is y, dy dx, equals the derivative of 109 is 0. So I took the derivative, I differentiated both sides with respect to x. Whenever I got to a y here, I used the chain rule, took the derivative of y squared to 2y, multiplied by the derivative of the inside, dy dx. All right. Now I need to collect dy dx terms on one side of the equation. They actually already are, so that's not too bad. But then I want to move everything else to the other side of the equation. So I want to leave 2y dy dx. I'm going to subtract 50x to the other side, 50x. Now I'm trying to solve for dy dx, right? So I'm trying to get dy dx by itself. I'm going to just treat this basically like its own variable. I can divide by 2y. That'll give me dy dx equals negative 50x divided by 2y. Negative 50 divided by 2 is going to be negative 25x over y. And there we go. We have dy dx, the derivative of y with respect to x, is negative 25x divided by y. Notice that my derivative over here, right, has both x and y in it. If I want to find dy dx, the slope, I would need to know an x and a y value to plug into here to find the slope of my original equation up here. I would need both an x and a y value to plug in. But that's the process. Take the derivative with respect to x, get dy dx by itself, simplify if we can, and that is our derivative. We did that implicitly. All right, let me do another example here. Let's find dy dx if we have y cubed plus y squared plus 5x minus 5y minus sine squared of x equals negative 4x squared. Notice I got y's and x's together on this side, so this is a great moment for implicit differentiation. If we ever see our y's and x's kind of together and they're hard to separate out, let's use implicit differentiation. All right, let's go term by term. The derivative of y cubed is 3y squared, but y is its own function. Remember, y is a function of x, so chain rule, dy dx. We're going to do this every time we get to a y thing. We take the derivative, and then chain rule will multiply by dy dx. Plus, the derivative of y squared is 2y. We'll take the derivative of a y, so I'm going to multiply by dy dx, chain rule. Plus the derivative of 5x is 5, minus the derivative of 5y is 5, because constant multiples stay. The derivative of y is dy dx. Minus, now I need the derivative of sine squared. We've seen that. That's a chain rule. We have Dorito squared, so it's 2, keep the inside. Bring down the 2 as power rule, 2 Dorito squared, so 2 Dorito, times the derivative of the inside, which is cosine of x, equals negative 4x squared. The derivative of that with respect to x is negative 8x. This is a little more complicated. So I have everything, I've taken the derivative of everything now. My job is to get, if I can, dy, dx things, all those terms together on one side and everything else on the other side. So let me do that. I want to keep 3y squared dy dx over here, plus 2y dy dx minus 5 dy dx. Notice I'm keeping all my dy dx terms still on the left-hand side. I want to move the 5 over to the right. So I want to subtract 5. That's going to be negative 8x. I'm going to move the 5 over there, minus 5. I'm also going to add 2 sine cosine of x, so plus 2 sine of x cosine of x. There you go. Notice I kept all my dy dx terms sort of together on one side over here. And I've moved everything else to on the right-hand side. Now I have dy dx in all these terms. Let me factor that out. I want to get just one dy dx up here. So I factor that out. That gives me 3y squared plus 2y minus 5 equals negative 8x minus 5 plus 2 sine of x cosine of x. All right. And I'm going to divide by this whole quantity here. If I divide by this, it'll leave me dy dx by itself. So I'll have dy dx. It's going to be equal to negative 8x minus 5 plus 2 sine of x cosine of x divided by that quantity, 3y squared plus 2y minus 5. And there we go. I've now solved for dy dx. Again, notice our final derivative over here is both x's and y's kind of combined together over here. I would need a point x comma y, the whole point, to plug in here to find the derivative of our original, more complicated function up here. All right, pause the video and try the practice problem you see underneath. Give that one a shot. All right, here we go. So in this case, 2y to the fourth plus 3x squared minus 3 equals 4x plus 2y. I want to determine dy dx. So I'm going to go through. I notice I have x's and y's kind of together, so I'm going to go ahead and take my derivative implicitly. Derivative 2y to the fourth is 8y cubed, but multiplied by dy dx, plus 6x, so that's just x values. Derivative of negative 3 is just 0. The derivative of 4x is 4. The derivative of 2y is 2 dy dx. All right, now we got to get our dy dx's together. Now it doesn't actually matter which side we combine them on. You'll end up with the same thing. I'm just going to move dy dx's to the left. That's just my general habit. So 8y cubed dy dx minus 2 dy dx. I'm going to move this term over here. Let me get this 6x term to the other side. So that'll be 4 minus 6x. I'll factor out a dy dx. That way I only have one of them left. I have 8y cubed minus 2 equals 4 minus 6x. Now I can divide by the quantity 8y cubed minus 2. That'll give me 4 minus 6x over the quantity 8y cubed minus 2. And there we go. I've now found the derivative implicitly. Again, I have x's and y's together in my final sort of derivative answer over here. All right, so we've seen a couple practice, a couple examples. You've gotten a chance to practice. We do need to make sure as we work through implicit differentiation problems that we still keep in mind all of our other derivative rules. They don't go away just because we're doing things in implicit differentiation, or as I'll say, implicit differentiation land. Those other rules don't go away totally. We still have to recall them. So let's do one of those where we have to remember some rules. I want to take the derivative here of x to the fourth plus x squared y squared equals 4 plus y squared. dy dx, I want to find that, but I see I have x's and y's mixed together. All right, so x to the fourth, derivative of that is 4x cubed plus, now here's an interesting situation, x squared y squared. We have two things multiplied together, and we're trying to take the derivative of both of these. Remember, y is a function of x, so I am going to have to use my product rule. All right, so the product rule says keep the first times the derivative of the second, which would be 2y, but we're taking derivative of y, so dy dx. Plus, so I kept the first, derivative of the second was implicit, plus derivative of the first, 2x, keep the second, equals if the derivative of 4 is 0, the derivative of y squared is 2y dy dx. All right. So now we've already done our derivative here. We got to get our dy dx things together on one side. I'm going to get them on the left and move everything else over to the right. That's just my normal pattern, like I said. X squared, that should be x squared times 2y dy dx. I want to subtract minus 2y dy dx to the left. That means I'll subtract minus 4x cubed to the other side. And minus 2xy squared to the right. I'll factor out my dy dx. That'll give me x squared 2y. Because I factor out dy dx, x squared 2y minus 2y equals negative 4x cubed minus 2xy squared. So dy dx, when I divide by my quantity here, will be negative 4x cubed minus 2xy squared over the quantity x squared times 2y minus 2y. Cool. And there we go. So in a situation like this, we just need to make sure we do our product rule, okay? Cool. So we've seen now an example of we have to keep in mind things like our product rule, but that applies to all the rules. We have to keep in mind things like our chain rule. We have to keep in mind things like our quotient rule. But for now, go ahead and practice this one. Okay, pause the video, give number 3 a shot here, see what you can do. All right, here we go. dy dx. We want to take the derivative here. It's going to be implicit because I see x's and y's kind of mixed together. I've noticed here, if I just kind of look big picture, I have some product here, x squared y, and another product here, negative y squared x. So I got to be careful. Okay, let's take our derivative, but we start with the product rule. I'll keep the first. The derivative of y is 1 multiplied by dy dx. So I kept the first, derivative of the second, plus derivative of the first, keep the second. Again, that was a product rule. Keep the first, derivative of the second, plus derivative of the first, keep the second, plus, well, the derivative of 2 is 0, so I'm just going to leave it. Oh, I got another product over here. I keep the first times the derivative of the second. Derivative of x is just 1 with respect to x, right? The derivative with respect to x of x is just 1. So I keep the first, derivative of the second is just 1, plus derivative of the first, that'd be negative 2y, but that's kind of annoying to write out. So what I like to do with these products when we have a negative sign is I just like to go ahead and make it negative there. So negative 2y dy dx. Took the derivative of the first, keep the second. All right, so we've now done our implicit differentiation. Let's isolate dy dx. So I'm going to move, again, dy dx is to the left-hand side. So that's going to be x squared dy dx plus 2yx. I'm going to move this x on the other side of dy dx just to be organized here. Dy dx. I added this to the left-hand side. Equals, I'm going to subtract 2xy over to the right-hand side, minus y squared. All right, so now I've gotten my dy dx's together on one side. Now my job is to factor out dy dx. That'll give me x squared plus 2yx equals negative 2xy minus y squared dy dx then is going to be equal to, I'm going to divide this quantity over to the right-hand side, negative 2xy minus y squared over the quantity x squared plus 2yx. And there we go. Again, we got to be on the lookout for these rules like product rules in there. Okay. Now we can also put these things to work. I know we're just kind of getting introduced to this idea today, but let me give you some examples here. Sometimes we will actually not need to explicitly solve for dy dx. Sometimes we may just want to actually find its value at some point. So in an example, if we're trying to just find a derivative or write the equation of a tangent line at some point, we don't necessarily need to solve for dy dx per se. Let me show you some sort of ways we can approach this. Okay? I'm actually going to do example 5 as our practice here. Let's say we want to find the slope of the tangent lines. Oh, that's interesting. It says tangent lines to the ellipse here at x equals negative 1, and then write the equation of the normal line at x equals 1. All right. So I want the slope of the tangent line. That sounds like a derivative, right? But if I look over here, my derivative will need to be implicit because I got x's and y's together. So let me do my implicit differentiation. The derivative of x squared is 2x minus, oh, we got a product, so keep the first, derivative of the second, plus derivative of the first, which is negative 1, keep the second, plus 2y dy dx equals 0. Again, 2y dy dx came from the derivative of y squared, and then derivative of 7 is 0. Okay, so I've done that. Now here's where things are interesting, right? In the end here, I want to find the derivative or the slope of tangent lines. Now if I solve this, notice I'll have x's and y's that end up on my right-hand side. All I have here is an x value. Wow, that's a hideous looking arrow. All I have here is an x value. That means I need to find a y value that goes with it. To find the y value that goes with it, just like normal, I can plug it into my original equation. Negative 1 squared is 1, minus negative 1, so that'll be plus y squared equals 7. If I subtract 7 over to the left-hand side and rearrange, I get y squared plus y. Subtract 7 over here, 1 minus 7 gives me negative 6 equals 0. So how do I solve for the y value here? Well, I can factor this, y minus 2, y plus 3. And what I realize now is actually there are two y values. Y can either be 2 or negative 3. So wait a minute. What that means is I actually have 2 points where I have tangent lines. Negative 1, that's my x value, negative 1 comma 2, and negative 1 comma negative 3. That's why they said tangent lines, because I end up with two y values to go along with this negative 1 point here. This is going to be some equation, that's not actually a function, that at some x value, there's actually two y values that correspond with it. So now I have my points. Here's how this can be easier. We can either solve for dy dx, or you can just plug in these points. If you want to, you can plug in negative 1, you can plug in 2, and then solve for dy dx. You can plug in negative 1, negative 3, and then you can solve for dy dx. You can plug these points in now. Or we can do what we did in previous examples and actually solve for dy dx. I'll do that, but the other way is totally fine too. So I'll say negative x dy dx plus 2y dy dx equals, I'm going to subtract 2x to the other side. I'm going to add y to the other side. That's a weird looking myself. It's minus 2x. I added y to the other side. I can factor out my dy dx. That leaves me with negative x plus 2y. Equals negative 2x plus 1. I say 1, negative 2x plus y. Sorry about that. So I factor out dy dx. I'm going to divide my quantity to the other side, so I now have negative 2x plus y over negative x plus 2y. All right, there we go. Now I can plug my points in over here. So my points, I'm going to change the color on this one. My slopes will be, if I plug in negative 1 for x and 2 for y, I end up with negative, sorry about that. Plug in negative 1 up here, negative 1 times 2 will give me 2 plus 2 over 1 plus 4 equals 4 over 5. So I have a slope of 4/5 that comes from this point when I plug this point in over here. I also have dy dx. If I plug in negative 1, negative 3 over here, I'll get 2 minus 3 over 1 minus 6. So 2 minus 3 will give me negative 1. 1 minus 6 will give me negative 5. So I have a slope coming out of here as at 1/5, positive 1/5. When I plug in negative 1, negative 3. All right, so I have these slopes. Now I can write the equations of the tangent lines. This first tangent line came from this point up here. So y minus y1 equals m over x, m times x minus x1. So minus -1 gives us +1. And then this tangent line would be from this point over here. So the tangent line would be y minus y1. So y minus -3 gives us y plus 3 equals m x minus minus x1. So x minus -1. And there we go. So these would be our tangent lines. Then we could write the equation that should say normal lines. Sorry, the equation of the normal lines. We could do the normal lines from here too. Cool. So we can use implicit differentiation to also find the stuff we have already found, like tangent and normal lines. One last example I want to show here, and then the rest of the time will be a chance to practice a little bit. Okay. Actually, yeah, we may do one quick thing afterwards. All right. So what if we want to find higher order derivatives, though? What if we want to find something like a second derivative at x equals 1 for this function? Well, we always start by taking the first derivative. I see I have x's and y's together, so let me go ahead and do this implicitly. All right. So the derivative of x cubed would be 3x squared, plus the derivative of y cubed would be 3y squared, dy dx, because I'm taking the derivative of a y thing, equals 0. Now, I'm going to go ahead and get dy dx by itself. But you might go, well, why can't I just do the derivative here? Yes, but you end up with some sort of complicated looking stuff. So what I often recommend is actually, let's just go ahead and solve for dy dx right now. I'm going to subtract 3x to the other side. I want to subtract 3x squared to the other side. I want to divide by 3y squared. I'm going to end up with dy dx equals negative 3x squared over 3y squared, which is going to give us negative x squared over y. All right. Now that I have this, here's what I can do. To get to the second derivative level, I need to take the derivative of this thing again. So if I want to get the second derivative, I need to take the derivative of negative x squared over y. But look at this. This is a quotient now. So I'm going to use the quotient rule. Y, so I'm going to do low times the derivative of the high minus high times the derivative of the low. The derivative of y is dy dx. So low d high minus high d low all over low squared. But we can't stop here because notice I have a dy dx in here. So what I need to go back and do now is, do I know what dy dx is? I do. It is this. So I go back and I substitute, and I want to clean up this front part too. Negative 2xy plus x squared. Dy dx is negative x squared over y. Notice I just substituted what I knew dy dx was in for the dy dx, all over y squared. And here then is my second derivative. So I did my normal steps, found dy dx, took the derivative again using the quotient rule, and then substituted in what I knew dy dx to be. And that's how you do that. That process can be used to find the second derivative for these functions. I do want to mention one comment before I talk about the homework real quick. Let's say we want to find, I should also say, I apologize, that I know we wanted to find the second derivative at x equals 1. If you want to do that at this point, we plug in 1. We'd solve for y. I guess I could back up. Right, we would plug in 1 up here, and if x is 1, we get 1 plus y cubed equals 9. So y cubed equals 8. So y equals 2. And now I have the point 1 comma 2, and you can plug that in down here. Sorry about that. Got ahead of myself. I want to show one thing about example 3 here that just to keep in mind. Let's say we want to find the second derivative, and we have this function here. Now this is kind of interesting. We have y minus 3 squared plus x squared equals 9. Now implicitly, this is interesting because I have this as a chain rule actually, don't I? I have Dorito squared. So I go to take its derivative, I'd have 2 Dorito, right? Take the derivative of the outside, squared, keep the inside, times the derivative of the inside. The derivative of the inside is 1, but we took a derivative of y, so the inside is dy dx, plus 2x equals 0. And then you can continue this process like we normally have done. So don't forget about just your general chain rule rules. All right. For homework tonight and over the weekend, this is what I want you to do. I want you to do the implicit differentiation practice you see here. It's going to ask you to find 4 derivatives, first derivatives. I want you to find a second derivative. And then I want you to find the equations of the tangent normal line to the curve given here at 1, 4. Okay? Do those then, and then my answers will be up online sometime Friday, Saturday. You can correct your answers in a different color and upload them to the assignment for lesson 3.3. There's optional homework below, and you can get started on the con if you would like to. All right, talk to you later. Bye.